this value and this value isn't exactly 0. It doesn't mean it's big, it doesn't mean it's important. But let's go ahead and find out, how unlikely would it be to get a mean this far away from what we expected 100 if the truth were the population means 100. And that's what Minitab gives us here as the p-value. If you look at your output, oh, here's something else notable. Look at what the standard deviation, the sample standard deviation is that Minitab gives us here. Look right beside the mean there, Tim. 12.98. Now, notice we told Minitab to assume that it's 15 in the population. It came out around 13. Now that's real close. But it might make more sense, since we have a standard deviation from the sample that we could use to estimate the population standard deviation, to use that. And that's what we're going to do next when we do this with T. So Minitab uses this mean, this standard deviation. It computes the standard error. If you look at the standard error of the mean there that Minitab gives us, you'll see that it has just taken the standard deviation divided by the square root of, it was what, 88 scores? 88 scores. And that's how it got the standard error. And then it took the difference between the mean, sample mean, that and the null, and divided by that standard error, and got the z-score. The standard deviation is used here, 15. Got the z-score. What was the z-score there, Ken? 10.16. Now, if the null is true, the z-score you expect to get is going to be about 0. This is about 0. What's the probability of getting the z-score that far away from 0? That's our exact significance level t, and that, Tim, is 0.87. And the decision rule that we usually use, by tradition, unless we want to think about the consequences of type 1 and type 2 errors, is if that t-score is less than or equal to 5%, then we reject the null hypothesis. In this case, conclude that the population mean is not 100 in Vermont. If it's greater than 0.05, then we do not reject that null hypothesis. In this case, then we're going to not reject the null hypothesis. We have cast very little doubt on this null hypothesis. And in terms of a summary statement, we might say the mean IQ of students in Vermont was not significantly different from 100, comma. Now, we should give the sample mean and standard deviation. We could do that right here, or we could do it up here, right after mentioning the variable. I'm going to just go ahead and do it here. Means equal to 100.26. Standard deviation is equal to 12.98, comma, test statistic z. Now, z doesn't have degrees of freedom. Somehow we have to indicate how large our sample was. So we'll simply say n is equal to 88. Now the value of z, 0.16. And the value of p, 0.87. And then you've got a pretty complete, but still terse, summary statement that identifies what statistic are we testing? Mean. What's the variable? IQ. Who were our subjects? Students in Vermont. What hypothesis were we testing? Average is 100. Did we reject the null hypothesis? No. It's not significantly different from 100. The sample statistics. Test stat used. N value of test stat. P value. Lots of information there. Questions on that one? You got your check, Ken. You did good. But add it down. interesting there, Terry? Take a look at the next command that we had. It's a zint command. This will do a confidence interval for us. If we don't tell it how much confidence we want, it'll do 95%. We can tell it what, and I actually did there. I said, give me a confidence interval using Z, 95% confidence, assume standard deviation 15, use the data in column 4, and Minitab gives me the mean and standard deviation, all that stuff again that we already got from the Z-test. But at the end of that, you'll find in parentheses the 95% confidence interval. Give me that confidence interval.
97.12 to 103.
97.1 to
97.12.
12 up to
103.40.
103.40.
Yes.
Okay, take a look at that confidence interval. With the data that we have now, using this analysis by Minitab, we're 95% certain that the true value of the population mean IQ of students in Vermont is somewhere between about 97 and about 103. Well, that tells us this is a pretty average population. And if someone were to ask us, well, are they average? And you say, well, what's average? And you say, about 100. You say, yep. I'm confident it's somewhere between 97 and 103, and both ends of that are real close to average, 100. And if someone asks you, well, is it significant? And you say, you mean if I tested the hypothesis that it was exactly 100, I would not reject that hypothesis? Or I would reject it? You would not. Not significant. Because that 100 is included in there. Again, we could make essentially the same conclusions that we made with hypothesis testing using nothing more than this confidence interval. That's not the way behavioral scientists typically do their statistics, but it's the way I think they ought to. And maybe, I'm getting a little more hopeful about this now, maybe 5-10 years from now it will be. I sent you all an email about an article that appeared in an American Psychologist recently. That article is available online if you'd like to look at it, and I put a summary of it on the web. And one of the things that they recommended was that hypothesis testing only be used in the circumstances where it is the most appropriate analysis for behavioral data. And it is not always the most appropriate analysis, and they encourage doing things exactly like this. This article, by the way, was written by a team put together by the American Psychological Association of highly respected, eminent statisticians. They really didn't say anything that statisticians haven't been saying for many years. But now they've got the force of the American Psychological Association behind them. They're publishing a journal that every member of that association receives. And maybe it will have some impact. I'm not terribly hopeful that it will. There's a lot of inertia. And when people have learned to do something one way, and they've been doing it that way for many, many years, when someone comes up and says, there's a better way to do this, let me show you how. Initial reaction is likely to be, I'm happy doing it the way I am. I don't want to learn a new way to do it. We'll see. We'll continue to learn both the old and the new way in this class. So you'll be able to interpret the research literature regardless of whether it changes or not. Other than giving us the confidence interval, this zint command gives us just the same information that we got from the Z test command. Now, with the Z interval command, we have the same problem that we have with the Z test command. That is, it assumes we know what the population standard deviation is, which is kind of a ridiculous assumption. Why would we be estimating the population mean if we knew the population standard deviation? If we knew the population standard deviation, then we must have the whole population of scores, and we don't need to estimate its mean. We can figure out exactly what it was. So what would actually be done here, in a typical research situation, is we simply replace Z with T, both for the hypothesis test and the confidence interval. In terms of the computation, the only difference is in computing the standard error of the mean, the standard deviation of the sampling distribution, instead of using the value 15 that we give Minitab, it will use the sample standard deviation computed on the data. Instead of reporting a Z, it's going to report a T. Instead of using critical values of Z to set up the confidence interval, it'll use critical values of T. When using T, it'll deal with the degrees of freedom, and it'll tell you what the degrees of freedom are here, and it better tell us that they're 87 since we had 88 scores. Well, let's take a look at that output. And this is the command that immediately followed the Z interval command. We told Minitab t-test t-test, that's the hypothesis that the mean is 100. We don't tell it a standard deviation anymore, but we still tell it which column has the data. Take a look there, Amanda, and tell me what did Minitab give us for the value of T?
0.19.
0.19, yes indeed. That's almost the same as the value of Z that we got. And for the p-value, instead of 0.87, what did it give us?
0.85.
0.85. Nearly identical results. Our summary statement over here also is going to be nearly identical. The mean IQ of students in Vermont was not significantly different from 100. The mean still the same. Standard deviation is the same. Instead of Z, we're using T. T has degrees of freedom. That also tells us the sample size if we add 1 to it. T, a little bit bigger than the Z, because the standard deviation was smaller than 15. And the P, a little bit smaller, but still not very strong evidence against IQs in Vermont being other than 100 on average. And Amanda, look down at the next one and tell me how the confidence interval changed. Instead of about 97 to 103, what did it come out to be?
97.51, 103.01.
That's using the P distribution and nearly identical again. And that pretty much wraps up one sample test. Thanks, Amanda. Any questions on the one sample t-test before we move on to two sample t-tests?
Okay, so when you say non-significantly different, then that means that, okay, you're going to accept that knowledge.
Exactly.
Okay. And then if you weren't going to accept, you'll say was significantly different.
You got it, exactly.
Okay.
Now,
Okay.
one small little point here. Some statisticians would be upset with the use of the word accept the null, because they think accept, and other statisticians use that language, but some don't like the language accept the null because that implies that you now believe the null to be true.
Okay, not rejected.
And they would prefer to say not reject the null. The next topic we're going to cover, and we may get started on the day, we may not, we're going to cover power analysis in detail. And I'm in the process of doing power analysis. I'm going to show you how you can actually accept the null in the sense of saying, you know, this null may not be exactly correct, but it's close enough that for all practical purposes it's correct. And essentially what this is going to involve is this. You ask me whether there's any fire ants on the mantle over there. Okay? If I'm standing over here, I've got my glasses, and I say no, you're going to say, you know, the null hypothesis is that there's no fire ants over there. You're going to say, I'm not really very confident. You didn't have much power. They could be over there, and there's a good chance you wouldn't see it. Type 2 error. I put my arm up there, I'll get bit. But if I put my glasses on and I come over here and I look on here and I say,